updating it fast to try and compete with Zoom, so it's better. But...
Okay. So I think we've drawn a really good crowd here. So it's so this is maybe it is time. So everybody, in case you haven't seen Richard Thomas before, that's him. That he makes a personal appearance in our seminar today, directly from London, and so I think in a second we'll see his slides up on the screen. Is that the plan?
Yeah, let's do that.
Yeah, and so then please give your complete undivided attention to the talk. Don't browse the internet.
Exactly.
Like Richard was complaining. Yeah, so
I allow it. You can browse the internet.
Yeah, I turn it over to Richard.
Okay, great. Thank you. Thank you very much for the invitation, Andre. Hi to everyone. Hi, Clara. Hi, Melissa. So I'm going to talk about counting sheaves on Calabi-Yau fourfolds, or at least that's what I'm aiming for at the end.
We don't see your slides yet. Is that?
You don't. Oh, I'm so sorry.
No. Yeah, Zoom hasn't filled. You have to give at least the first slide, and then the Zoom can fill in the rest. Yeah.
How's that?
Oh, that's great. Yeah. Then I can...
Okay. Good. So Borisov-Joyce defined a way to count sheaves on Calabi-Yau fourfolds about 5 years ago using derived differential geometry and real numbers, which I was unfamiliar with until their paper. So obviously, and so what they define is basically incomputable. It's not possible to compute with. So the idea of this project is to define something within an algebraic geometry that you compute with. But mainly my talk is going to be about orthogonal bundles. And these are not the same bundles that I'm counting on Calabi-Yau fourfolds. So don't be confused. These have nothing to do with Calabi-Yau fourfolds yet. So I'm just going to talk about orthogonal bundles and special orthogonal bundles on schemes or algebraic varieties. And the Edidin-Graham class, which is some kind of square root of the Euler class. So the talk is mainly going to be a talk about a very nice characteristic class and how to localize it, just as the ordinary Euler class can be localized to the zeros of a section. The correct thing to do here is to localize to the zeros of an isotropic section. So isotropic is the natural condition to put on a section when your bundle has an orthogonal structure or a quadratic form on it. I'll define isotropic, I'll remind you what it is. And from that, I will explain what that has to do with counting sheaves on Calabi-Yau fourfolds. As I say, the sheaves are not the same as the orthogonal bundles. The orthogonal bundles will arise as an auxiliary thing on the moduli space of sheaves on a Calabi-Yau fourfold. And the result is done in algebraic geometry in the Chow group, whereas Borisov-Joyce work in homology. And we proved that our class, when you pass to homology, is the same as Borisov-Joyce's class, up to inverting 2 in the coefficients. But we won't worry about that. You'll see where that comes in. And then I'll briefly describe a K-theoretic Euler class. I'll remind you, I'll explain what that means. And then I'll define the analogous square root Euler class, and I'll also localize that to the zeros of an isotropic section. And this will allow us to define a virtual cycling K-theory, or a virtual structure sheaf on the moduli space of sheaves on a Calabi-Yau fourfold. And it'll be related to the previous construction by a virtual Riemann-Roch formula. And I'll give you a torus localization formula for both of these classes, which makes them computable. So that's the plan of the talk. But for now, forget about Calabi-Yau fourfolds. This is just to talk about orthogonal bundles. So I'm just on a quasi-projective scheme with some holomorphic or algebraic vector bundle on it with a quadratic form, non-degenerate, holomorphic algebraic quadratic form. And so by the Graham-Schmidt process, it's étal locally trivial, not necessarily Zariski locally trivial, because if I try and find an orthonormal basis for this quadratic form, it'll involve taking square roots. So I have to pass to a double cover before I can do it. Okay, so these quadratic bundles correspond to étale locally trivial principal orthogonal bundles, ORC. ORC is the symmetry group of C to the R with the standard quadratic form on it, you know, sum zi squared. All right, and then that quadratic form gives you an isomorphism by contracting with it between the bundle and its dual, a holomorphic algebraic isomorphism. In particular, the determinants are the same, and therefore the determinant of my bundle is canonically has square trivial. And an orientation, so this is not orientation in the usual sense, but an orientation in this sense is a trivialization of the determinant of my quadratic bundle, such that that trivialization squared is this star here. Okay. So it's a Z mod 2 choice. So it's not like usually when you trivialize the determinant of a bundle, a complex bundle, it's a C star choice. But here it's a Z mod 2 choice because we already have this trivialization of the square and we want to be compatible with it.
So Richard, why is that
oriented?
Why is that a Z mod 2? I thought it's like peak, 2 torsion and peak or something like this. Is that not?
No, that's the obstruction. And I'm talking about a choice of orientation if it exists.
Oh, okay, okay, thanks, yeah.
And because I've called it O, it looks very much like an obstruction. I beg your pardon, that's a great point. Okay, so you're right, the obstruction is 2 torsion in pick. I'm assuming the obstruction vanishes. And so what I'm going to be interested in is bundles for which the obstruction vanishes, and then I have a choice, and it's a Z mod 2 choice. Yeah, thank you. Okay, so really what I'm interested in is étale locally trivial principal SO-RC bundles. Okay, so SO-RC, as you know, is R by R complex matrices, preserving the standard quadratic structure on C to the R, but also with determinant 1. And they correspond to these oriented orthogonal bundles. So orthogonal bundles with a choice O is this orientation. Okay. And then this is motivation if you're happy with the real numbers. If not, don't worry, you can ignore this slide. But orthogonal bundles are maximal real positive definite subbundles. Okay, so a real subbundle of half the dimension, on which the quadratic form is just a real quadratic form and it's positive definite. So it's an inner product. Okay, so you should think of, you know, the real slice, the standard real slice in C to the R, where all coordinates are real, that's maximal positive definite for the standard quadratic form. Okay, so if I expand sum zi squared out in terms of xi's and yi's, I get this quadratic form. And if I set the y's to 0, then I just get sum xi squared. So I just get the standard real positive definite quadratic form, 1r to the r. All right, and conversely, given a real bundle with a real inner product, a quadratic, positive definite real quadratic form, I get a complex bundle with a complex quadratic form by tensoring. Okay, so it's the quadratic form's positive definite on this piece and negative definite on this piece because I squared is -1. So in other words, complex quadratic bundles are the same thing up to homotopy as real quadratic bundles. Okay, and that's because there's, you know, that's a reflection of this homotopy equivalence between these groups. And there's similarly a homotopy equivalence between the special version of the groups. And what that corresponds to is that the orientation on the previous slide correspond to orientations in the usual sense on the real bundle. And in fact, here's a description of that. So if you pick orthonormal basis, then you can write the orientations in the usual way. So if you take this orientation on the real bundle, it corresponds to this, I beg your pardon. If you take this orientation on the complex bundle, then you get this orientation on the real bundle. Okay, so more or less, up to homotopy, characteristic classes, and so on. These bundles, these SORC bundles, are just the same thing as real-oriented bundles. Okay, and why did I say that? Because real-oriented bundles, as you know, have a standard characteristic class, which is their Euler class. Okay, if they're odd rank, then the Euler class is 2 torsion. So I'm not going to consider odd rank now. It's important that we do in our paper, but for this talk, I'm going to consider even rank. So now I could just take the Euler class of that real bundle, and that's some kind of characteristic class of my original bundle. And it satisfies this identity that its square is the Euler class of the complex bundle considered as a real bundle. Okay, because the complex bundle is, so E is a copy of ER, the real form of E, plus I times ER. And you have to worry about the orientations, and that gives you this sign, but let's not talk about that. So this is why we call it a square root Euler class. Okay, so this is just topology for now. So we've got this characteristic class in homology, in cohomology, and you could ask, is it algebraic? Can you lift it to Chow cohomology? And Field and Totaro showed you cannot, but Edidin and Graham showed actually you can, up to sign, and the sign will be very important for us, so we'll fix the sign in a bit. Let me just check something. Yeah, that's fine. So they showed that it can be constructed in algebraic geometry. So obviously not by the method that I've been describing, which was using real geometry. So what they do is, in place of these maximal positive definite real subbundles, they use maximal isotropic holomorphic subbundles. So let me describe that. Okay, so a subbundle is called isotropic if the quadratic form restricted to it is identically 0, and maximal isotropic if it's of maximal possible dimensions, that's half. So these are like the Lagrangian subspaces of in skew or symplectic geometry. This is the symmetric version of that. So for instance, in C2 with the standard quadratic form, the real positive definite subspace was spanned by, 1, 0 and 0, 1 over the reals. And there are 2 isotropic vectors. So there's one I and one minus I, and that's all there is. And so you can take the complex span of either one of those, and you get a one complex dimensional maximal isotropic subspace. Okay, and I think I just said that. And this maximal isotropic sits inside the obvious exact sequence. When you take an element of E, by pairing it and evaluating it against lambda, that's therefore an element of lambda dual, and that projection to lambda dual annihilates lambda precisely because it's isotropic, and the sequence is then exact precisely because it's maximal isotropic. So you'll be more familiar with this exact sequence in skew geometry and for Lagrangian subspaces. And so what you find is that the top Chern class or Euler class of this maximal isotropic, if it exists, also squares up to a sign to give the Euler class of the rank 2n bundle E, the orthogonal bundle E, because the top Chern class of lambda dual is -1 to the n times the top Chern class of lambda. Okay, so this looks very much like the square root Euler class we were dealing with before. And notice that, again, when this maximal isotropic exists, you can map it to a maximal real subbundle in the following way. You include into E and then just project using the splitting of E into ER plus IER. And then that will always be an isomorphism, because the kernel would correspond to elements of lambda which were in I times ER, but the quadratic form is negative definite on I times ER, and it's 0 on lambda, so they can't intersect except to the origin. So you find that actually this lambda is isomorphic as a real bundle to ER. And so this is no surprise. Okay. So when E admits a maximal isotropic subbundle, it makes sense to define this kind of square root Euler class or Edidin-Graham class to be up to sign the top Chern class of lambda. And the sign is important because, because if I took sort of lambda plus lambda dual with its obvious quadratic form, the off-diagonal quadratic form, pairing lambda and lambda dual, then it has two maximal isotropics, or two obvious ones, lambda and lambda dual, and their top Chern class differ by a sign. So fixing this sign is tricky, and it's important for what we do later. So we do that. And now I'm going to tell you how we do it, and I want you to not look at it and immediately forget it, because you aren't going to absorb it in one sitting, and we're changing all our conventions right now, and we're going to repost our paper on the archive with all different signs. But anyway, there is a way of fixing signs. It's the following. The kind of takeaway message is that these maximal isotropics sit in two different families. There's the positive ones and the negative ones. So the orthogonal Grassmannian has two components. There's positive maximal isotropics and negative ones. And once defining what you mean by positive and negative is equivalent to picking an orientation on the bundle E. So because of this exact sequence, you get an isomorphism between the determinant of E and the determinant of lambda tends to the determinant of lambda dual, which is canonically trivial. And if the orientation goes to this number here under this isomorphism, then you call lambda positive, and if it goes to the opposite, then you call lambda negative. Okay, so there's a way of defining a sign for all maximal isotropics once you've picked an orientation on your quadratic bundle. And it's equivalent to the following. So if you don't mind real numbers, this is a much nicer description of it. What you should do is you should consider that isomorphism I told you about earlier between the maximal isotropic and the real subbundle. And I also told you that the strange orientation on E was equivalent to a usual real orientation on ER. And now you should ask, is this isomorphism here orientation preserving? Because this is oriented. And lambda is a complex bundle, so it has a natural orientation, real orientation. And you can ask, is this oriented, this map? And it's oriented if and only if lambda is a positive maximal isotropic. Okay, so, and then that fixes that sign. So now we define the square root Euler class to be the sign. So if lambda is a positive maximal isotropic, we just define it to be the Euler class of lambda. And if it's negative, then we put a sign in. Okay, and now this, remember this red, if here, this is, in general, these lambdas don't exist. In particular, when they do exist, E with its quadratic structure is Zariski locally trivial, so that's not all the time. But in general, what you can do, if you remember the splitting principle in topology, you can always pass to some kind of bundle or cover of your space on which your bundle splits into a sum of line bundles. There's a similar thing here where there's a certain tautological way to pass to a cover of your scheme so that E admits a maximal isotropic. So one way of doing that is the following. You just pick your bundle over Y to be the positive, the orthogonal Grassmannian, the correct component of the orthogonal Grassmannian of E. So what that means is fiber-wise, you replace the fibers of E by the space of all positive maximal isotropics. So that's some kind of Grassmannian, and it has a tautological positive maximal isotropic subbundle of the pullback of E on this thing. Okay, so this is just a tautological standard thing to do. And then upstairs, now you do have a maximal isotropic, so you can define the square root Euler class, and Edidin-Graham prove it descends. Again, they prove it mod a sign, but we fix the sign. And how do they prove it descends? They only prove it descends if you invert mod 2. I'm not sure I said this correctly earlier. Where were we? When we were talking about Totaro. Here. No, here. Okay, sorry. So Field and Totaro showed it doesn't lift if you use Z coefficients. I feel like I didn't make this clear before. But Edidin-Graham show it does lift if you allow yourself to invert 2 in your coefficients. And we're now seeing why this is. So let's go back here. So Edidin-Graham show that this class, which we've now got up on this cover or bundle over Y, it descends at least if we invert 2. So there's a distinguished class, cohomology class, on Y tilde, which has degree, which is finite over Y. So it has degree 2 to the n minus 1 over Y. So what you should think of this is sort of Poincare dual to this class. The Poincare dual to this class is a cover, a finite cover of Y. So cutting down by this class cuts Y tilde down to a finite cover of Y, and the degree of that finite cover is a power of 2. So what you can do is you restrict to that finite cover, push down, and all that does is it introduces this annoying power of 2. But if I'm allowed to invert 2, then that's not a problem. I can just define my square root Euler class to be 1 over that power of 2 times the push down. And then this has lots of nice properties. So we now have a characteristic class. Once we've inverted 2 in our coefficients, its square is the Euler class. Its pullback is the class we constructed. If E, rather than its pullback to this bundle, admits any other maximal isotropic, then this class is the Euler class of that maximal isotropic up to the sign given by whether the isotropic is positive or negative. There's a Whitney sum formula. It's equal to the topological class excuse me. You see, I talked to Andre for 5 minutes now. I've got me coronavirus. It's equal to the topological Euler class I was discussing before in cohomology, again with 2 inverted coefficients. Okay, so any questions? I summarize. I've defined you a characteristic class for special orthogonal bundles, so oriented quadratic bundles. There's too many adjectives in this subject. And I'm now going to describe how to localize it, but any questions?
Sorry, I missed. What is -1 to the power lambda?
Oh yeah, that was the thing I told you to forget. So thank you for paying attention to me and forgetting it. Where was it? It was defined here in terms of the orientation on E, and I told you that you couldn't possibly understand this sentence in one sitting. But I sent Andre the slides, and I can send you the slides. So if you wish, you can stare at this later. But it's just, there is a way of defining it in terms of the orientation on E.
I think the participants who listen to you now, they got 2 copies of your slides. So I think they're
great.
Well equipped to parse this.
Good, so they have no excuse to be browsing the web then. Okay, so now I'm going to localize these classes. So first I'm going to remind you, supposedly, about how you localize the Euler class, the standard Euler class. So if you have just a bundle, F, on a scheme and a section, so there's no quadratic structure at the moment. Now, the nice case is where the section's transverse to the 0 section of F. Okay, and in that case, its 0 locus is the Euler class. So we all know that. But even if not, Fulton-McPherson intersection theory gives you a class localized to the 0 locus Z. So this localized class, so this is the Euler class of F localized by S, is a class on Z. It won't be the whole fundamental class of Z, if Z has too high a dimension, if the section is not transverse, but it'll be some class cutting down Z further to a class that when you push it forward, it gives you the Euler class on Y. Okay, and how do they do it? So what they do is they take the graph and they kind of linearize it by deforming it to the cone. You should think of this as the normal bundle to Z inside Y, and that sits by a junction inside the actual bundle F. Okay, so what's the story? What you do is you take the graph of t times S and you take the limit as t tends to infinity. So you make the graph more and more vertical until in the limit it looks like the normal bundle to Z in Y sat inside F. Okay, so there's a picture. So the graph is the red thing. The dotted red thing, if you can see it, is sort of the graph of t times the section. And then we send t to infinity. So we make this graph more and more vertical. And in the limit, we get this vertical thing, which is a copy of something called the normal cone to Z inside Y. But it's just, you should think of it as the normal bundle to Z inside Y. But it's sat up inside the bundle F. And I've drawn this one thicker because I'm pretending this is some kind of fat point here where the section had some multiplicity. The zeros of the section have some multiplicity. You get this sort of thicker cone there. All right, so that's what Fulton McPherson do. And then they say, well, instead of intersecting the graph with the zero section, we can intersect this cone with the zero section. And now we're working entirely over the zeros Z. We're not working on Y anymore, we're just working on Z. And so we can intersect this cone with the zero section just over Z to get this localized Euler class. And that intersection is defined by something called a Gysin map. And if you know a bit of Fulton-McPherson intersection theory, then this is all boring. And if you don't, you're probably not going to get a very good feeling for it in 2 minutes. But that Gysin map is just the inverse of the algebraic version of the Thom isomorphism. So the Thom isomorphism goes this way. It says that the Chow cycles on Z, by pulling them back, give you non-compact Chow cycles on the bundle over Z, and that's an isomorphism. So you just take the inverse, and that's intersecting with the zero locus. Okay, so in other words, any cycle in the bundle over Z, like this red one here, is rationally equivalent to a cycle which is actually pulled back from Z. Okay, so even though what I've drawn here might not take up all of F, it might just, so that this might be the normal bundle to Z in Y sat inside as a subbundle of F, not the whole of F. But even though it is only a subbundle of F, it's rationally equivalent to something which is the pullbacks of some smaller cycle in Z, and that pullback is the whole of F. Okay, so I'll give you an example of it in the next slide. So when you get something called excess intersection, when this normal bundle sat inside F is not the whole of F. So when it's the whole of F, essentially you've got a transverse intersection, and the localized Euler class is just the fundamental class of Z. When it's a subbundle of F, then it has a quotient bundle. In general, everything's more complicated, but I'm just going to talk about, I'm going to pretend everything's a nice bundle. There's a way of doing it in general. And you define the excess normal bundle or the obstruction bundle to be the quotient. So what's left over? So this is the part of F that we haven't used at all. Our section, sort of, you imagine your section lived in a subbundle and it cut out Z as sort of some representative of the Euler class of that subbundle. But that's not the Euler class of F because we haven't used the quotient bundle yet. And when we do, what we find is that this localized Euler class is not the fundamental class of Z, but it's the Euler class of this obstruction bundle on Z. Okay, so the simplest way to understand that is when everything's split. So when F is just this normal bundle plus this obstruction bundle, and we haven't used this obstruction bundle yet. So when we do that Gysin map on it, well, there's a formula you definitely won't absorb if you've not seen it before. Then what you find is you end up with the Euler class of the obstruction bundle capped with Z. Okay, so this is what you should imagine is perturbing your section. Your section sort of just lives inside the first component. And what you should imagine is by perturbing it, by taking a section of the obstruction bundle as well. And if you do that, then you cut down the zero locus to not just Z, which is the zeros of your original section, but also the zeros of this perturbation in ob that you weren't using before. And that's what cuts you down to the Euler class of ob over Z. So that's the excess intersection. And if ob isn't a bundle, then there's a more complicated thing that Fulton McPherson show you how to do. Now, if you didn't follow any of that, I apologize. But there's a worse thing you can do. In many moduli problems, what naturally arises is not a section of the obstruction bundle, which is rather artificial. That arises mainly in differential geometry when you try and perturb things, but we don't like doing that in algebraic geometry because there's not many perturbations. But what often naturally arises, of course, in algebraic geometry is the dual thing. And the dual thing is what's called a cosection, or a section of the dual of ob. And then there's a way of localizing to the zeros of a dual of a cosection of a section of the dual of the obstruction bundle. And that's not surprising because the Euler class of the dual obstruction bundle is the Euler class of the obstruction bundle up to a sign. So it's not too surprising. The strength of the statement is that this is also true when ob isn't a bundle and when Z isn't nice and reduced in LCI and so on. But anyway, there is a way of localizing to a section of the dual obstruction bundle. And it was done by Keeman Lee. So I won't say too much about it other than just telling you their result, which is that they, instead of, when you want to intersect with the zero section of F by this Gysin map, what you can do is you can produce a refined class which doesn't just lie in Z, but it lies in the zeros of this cosection, so long as your cycle lies in a certain place. So long as your cycle lies in the kernel of this cosection map. So that would be a whole nother talk describing how they do that and how they localize. But hopefully, if you stare at this slide enough, in the case where the obstruction bundle is a bundle rather than a sheaf, this slide will make you believe that one should be able to do this, and that is what they do. Okay, and we're going to use this. So that will be the slightly technical part of the talk. And if you're completely uncomfortable with intersection theory, you shouldn't worry about it. You should just take it on trust. Okay, so here's how it goes. So here's the data. This is what we're going to do. Sorry, so did someone want to ask a question? Okay. So here's the data. We're going to start with one of these SON bundles, and we're going to have an isotropic section. And here's what's difficult is that someone's microphone is on. Does someone want to ask a question or turn their microphone off? Or maybe it's mine is doing something silly. Okay. We're going to have this bundle and an isotropic section. So not just any section now. And we're going to try and localize the Euler class, that's here, the square root Euler class, I beg your pardon, to the zeros of this section. Okay, so Z here are the zeros of the section. So that's what that's the main part of this part of the talk. That's the main construction, and it's quite technical. And if you don't follow it, I don't think it matters at all. The what should I say here? Even though it's an isotropic section, it would, in general, it will not lie in an isotropic subbundle, even locally. If it did, if the section is a section of an isotropic subbundle of E, then constructing this is much easier. You just localize the Euler class of the maximal isotropic to the zeros of this section. And that's all this construction will be. So if you like, just that should be motivation to think that this ought to exist. However, it is harder than that, because even locally, sections will not lie, isotropic sections will not lie in isotropic subbundles.
Well, how about if we constructed on some code, something that maps to y? Is that possible? Like the way you constructed the square root?
No, because if you at the zeros of s, if s is transverse, then it's all fine. If the moment s is not transverse, so even if s is just sort of quadratic along its zero locus, then essentially the directions of the quadratic, maybe I can give an example. Maybe not in public, I can't, but given 10 minutes, I could give you an example, but
it's okay, Richard, carry on with your plan.
No, it's fine, sorry. Anyway, yes, there you go. So the cone, yeah, let me answer that question in one slide's time. Okay, so the first simplification is, because we're using these coefficients, then we can pass to this cover, as Andre was mentioning. And so we can assume we have a maximal isotropic. We just can't assume the section lies in it. And now, because the square root Euler class is the Euler class of lambda, or lambda dual is more what will interest us here, what we can do is we can push the section down from E to lambda dual, consider it as a section of lambda dual, and then try and localize the Euler class of lambda dual to the zeros of the section. That's the first thing we can do. So we define this S star to be the projection of S, and we can localize the zeros of that, but they of course will be bigger in general than the zeros of S. So we won't be done when we've done that, but that's the first thing we'll do. So we do Fulton-McPherson theory. We linearize the graph of this S dual about its zeros, replacing it by this cone. And the way I was going to answer Andre's question is, if you did this with the full section, this cone could look like x times y equals 0. At a point, it could look like x times y equals 0 in C2. Give C2 the quadratic structure x times y, and then there's a cone x times y equals 0, and that clearly doesn't lie in any isotropic subbundle, because the isotropic subbundles are x equals 0 and y equals 0. And so that's fundamentally the issue here. That's the problem. In that particular case, you could split into two and do something, but in general, you can't. Okay, so that's the first thing. We remember, we take this graph, this nonlinear object, we linearize it, we replace it by this vertical cone. Cone just means it's C star invariant. Okay, and then we intersect it with the zero section. And so that's good. We've now loaded zeros of the projection of S. But we now want to localize it further to the zeros of S by using the other half of the section. So, our section, we projected it to lambda dual. Now we want to use the part in lambda. So how do we do that? What we do is we note that the section, once we restrict to Z dual, where its projection is 0, it now lies in lambda, because its projection to lambda dual is 0. And so actually it defines a cosection. So it defines a map from lambda dual, that was the bundle I was working in, to O. And the isotropic condition, this is where we use it. The isotropic condition on S means that the cone actually lies in the kernel of this map. And that's what means we can use cosection localization. So this is saying that this cone here is not using up the whole of lambda dual. It's not a transverse situation. There's some kind of co-kernel or excess normal bundle. And this here says that that excess, that quotient, has a natural cosection, a natural map to O. Okay, and so I can further localize this Euler class to the zeros of that. Okay, so and that's just the Keemly result that I was telling you about a few slides ago. And so that defines our localized square root Euler class. And if you're not really into intersection theory, I don't think you would have followed all of that, but that's absolutely fine. The diagram here is everything that you need to understand. There's a way, there's a square root Euler class of my quadratic bundle E, which maps me from cycles on Y to, which I can cap with to act on cycles on Y because it lies in cohomology. And there's a localized version which passes through the zeros of an isotropic section. And then when you push it forward, it gives you the square root Euler class of before. So that's all you need to take away from this. And then finally, another little thing, which is actually more useful for us, but is harder to explain, is that also, if you have an isotropic cone inside your orthogonal bundle, there's a square root Gysin map. So again, you should think of, here's what you should think of. In the nice case that the cone factors through a maximal isotropic, this is the usual Gysin map. This is just intersection of the cone or cycles on the cone with the zero section of your maximal isotropic. But in general, there is, so this square root is always that I'm kind of halving E into lambda plus lambda dual, roughly, is what you should think. But the cone won't in general lie in lambda, and in fact, it won't lie even locally in any lambda, but you can still define this map, okay? And very quickly, there's a tautological construction. Given what we've already done, it's very simple. You work on the total space of the cone. Up there, the pullback of E has a tautological section because the cone lies in E. So I'm on the cone, I'm at the point of E. So I have a tautological section of the pullback of E. And that's isotropic. That's basically what an isotropic cone means. And its zero locus is precisely the zero locus of my cone. And so we can just define the square root Gysin map to be the operator, which is the localized Euler class. Ooh, that should be the pullback of E. Localized by this tautological section. Okay, so, but there is such an operator. I feel sure I've lost most of you. It has good properties, again, a Whitney sum formula, compatibility with the previous class, under deformation, and so on and so forth. Okay, so so any questions? I'm now going to tell you, before I tell you what on earth all of that has to do with sheaves on Calabi-Yau fourfolds. Okay, so here we go. We start again. Pick a Calabi-Yau fourfold and some charge. You can pick sheaves with this charge or Chern character. And we're going to simplify things. We have to, we don't know how not to yet. We're going to assume that any semi-stable sheaf is actually stable in this class. We have a moduli space projective of stable sheaves of this Chern character. And its deformation theory is governed by the following. So at any point, any sheaf, because it's stable, its automorphisms just look like the multiples, that should say endomorphisms, should just looks like multiples of the identity. So more or less you can ignore them. So forget them. Its deformations are governed by x1 from F to F. Its obstructions are governed by x2. And their duality tells you that x2 is dual to itself in a symmetric way, not an anti-symmetric way. So this x2 vector space is a quadratic vector space, and that is fundamentally what this problem has to do with the rest of the talk. And then the higher obstructions, x3, they're dual to the deformations, so they don't vanish. Again, that's Serre duality. And what that means is that there's no Lee, Tian, or Behrend-Fantecchi virtual cycle. So all the usual tools mess up. And then there's even higher obstructions in Ext4, but again, you can ignore them because they're constant, because they're Serre dual to these endomorphisms here. Okay, so everything messes up. So what's the picture? What's going on? What's going on is the following. It's that the moduli space, you should think of it as being the zero locus of an isotropic section of an orthogonal bundle over a smooth ambient space. Okay, so this is how you should think of the moduli space, is being sat inside some smooth ambient space with an orthogonal bundle over it, an isotropic section, and M is the zero locus of that isotropic section. Okay, and this is actually globally true if you allow A and E to be infinite dimensional, and that's via gauge theory. So A will be some space of connections, E will be some space of two forms where the curvature takes values, and so on and so forth. And it's locally true. You can do it algebraically if you use these theorems of Boazes, Granovsky, Ben Bassett, Brav, Bussy, Joyce, Pantev, Toan, Vetsozi, Vaquier. So what they show is that locally, you can take the ambient space. So in a small neighborhood of your point F in M, you can take the ambient space to just be the vector space, the Zariski tangent space, the moduli space, X1FF. So that's smooth. And your quadratic bundle could be the trivial bundle with fiber X2FF. And as I said, that's quadratic by Serre duality. And then locally, the moduli space will be cut out of that Zariski tangent space by an isotropic section. Okay. What this corresponds to, if you're a deformation or obstruction virtual cyclist like myself, what this corresponds to is that the usual obstruction theory, so this complex over the moduli space, which globalizes these X groups here, takes this form. Its Serre duality tells you that it has a certain self-duality, and it takes this form coming from this diagram here. You know, you take the tangent space to A, you linearize this picture here. You take the tangent space to A, restrict it to M. You take the derivative of the section, that goes to E. And then there's a third term, and that's why there's an X3 and so on. And that goes back to the dual of this one here. And because E is isomorphic to its own dual, you can make sense of this dual map here and make sense of the fact that when you dualize that complex, it becomes itself. This flips back to here and so on. So a perfect obstruction theory, which is what Behrend, Fantecchi, Lee, Tian deal with, would be the case where this last term vanishes and you just have two terms. And the obstruction bundle would be the sort of the co-kernel of this ds. And we're not in that situation. So what's going on is really the equation S is taking values in the kernel of this ds dual. And the problem is, that's not a vector bundle. It jumps around, it's a sheaf. And so you don't want to try and truncate this complex or anything. You don't want to, you know, so this section is not taking its values in E necessarily. That, I mean, it is, but that'll give you the wrong answers. It's taking its values in the kernel of applying S again to E because of this QSS equals 0. Okay, so somehow we want to halve everything, cut everything down, cut this complex down to half its size and so on, cut E down to half its size to sort of be living, to deal with this fact that S isn't arbitrary, but it's isotropic. We want to cut down by this QSS equals 0. So we want to cut E down to sort of the kernel of QS comma blank. Okay, so, but morally, that's the picture, okay? And even though globally in algebraic geometry, this is not the picture here, that's only an infinite dimensional picture. Globally in finite algebraic geometry, this is the local picture, and its linearized version, which is this complex here, this does globalize. So even though A doesn't exist, this bundle here, this complex of bundles here, that does globalize. Okay, so and then also I haven't told you how to orient all this, but by other work of Joyce and Chow and Gross, you can orient all this, so I won't go into that. Okay, so we can't patch the local models together to try and do what we want to do, but what we can do is we can patch together the linearized version, which is essentially this complex down the bottom here. Sorry, I keep pointing at things and you can't see me doing it. So it turns out what we can do is patch the linearized version, and in particular the cone, which is the limit of these graphs, the vertical version of these graphs, is an isotropic cone in my bundle E that we can globalize. We can show those do patch together. So what you do is you end up with, even though you don't have this picture here, when you take the limit as s tends to infinity, as t times s as t tends to infinity, and you end up with a vertical, instead of a graph in here, you end up with a cone. You can globalize this. You get an isotropic cone in a quadratic bundle, an SO bundle, and you just define the virtual cycle to be this Gysin map applied to that cone, the Gysin map, sorry. So we're just taking, we're localizing, maybe I go back. Usually the Euler class, the Behrens-Fantecchi Euler class will be, roughly speaking, the Euler class of this bundle localized to the zeros of S. And what we're doing is taking the square root Euler class of this bundle localized to the zeros of S, which is the moduli space M. Okay, so again, just for the virtual cyclists, what we're saying is that the Lee, Tian, Behrens-Fantecchi virtual cycle would be the wrong thing to do. It corresponds to taking this stupid truncation of the deformation obstruction complex, and that's not a quasi-isomorphism invariant thing to do. It gives the wrong virtual dimension, which it gives a virtual dimension which varies from point to point. It doesn't make any sense. But instead, we halve this complex by, roughly speaking, throwing one bit away and replacing E by half of E by replacing it by a maximal isotropic. But in some sense, we use all maximal isotropics at once because ds does not lie in any given isotropic. Okay, and instead what Borisov and Joyce do, roughly, is they intersect this cone with the real subbundle, or the zeros of the I times ER. But we're using maximal isotropics. Okay, so they're halving the deformation complex by replacing E by its real part. And we show the result is the same. In particular, when you have odd rank and odd virtual dimension, their class is some power of 2 torsion, or it's 0 in rational cohomology. Right, do I have any time left at all to just flick through Euler classes? Okay.
Well, you have 35 minutes.
Oh, really? Oh, wow. That's far too long.
You don't have to use them all, but in principle.
I refuse your kind offer. I will talk for 5 or 10 more minutes. Okay, I'm sure everyone's deep into the Guardian website by now. You've got an exciting election coming up. Right, so I just remind you what K-theoretic characteristic classes look like. And I appreciate a reminder in the mathematician sense that nobody knows what they are. So K-theory is a generalized cohomology theory. So it satisfies all the axioms of a cohomology theory except the dimension axiom. And it has a theory of Chern classes. And these are very beautiful. They're nothing frightening at all. So in particular, there's a K-theoretic notion of Euler class. So what does that mean? It means a version of the Euler class of any bundle which doesn't lie in ordinary cohomology, it lies in K cohomology, in K-theory. And what is it? It's just more or less the same as the Euler class in cohomology. In cohomology, what do? You take the 0 section of your bundle and you intersect it with itself, or with a perturbation of itself, given by a section of the bundle in homology. Here we do the intersection in K-theory. So what that means is we replace the 0 section by the structure sheaf of the 0 section. That's what this is. And you intersect it with itself in the sense of just taking tensor products of structure sheaves. So you just take the structure sheaf of the zero section, you take its derived tensor product with itself, considered as an element of the K-theory of E, and you end up in the zero section, in other words, in Y. Okay, so you pull it back via just pull back on sheaves to the zero section of E, and you end up with a class in the K-theory of Y. Okay. So you can give an explicit formula for it. It's just the alternating sum of the exterior powers of E dual, just by the Cazal resolution. And even better, when E admits a transverse section, this is just the Cazal resolution of the structure sheaf of the zero section of the section. Okay, so whereas in homology or cohomology, the Euler class is the fundamental class of the zero section, in K-theory, it's the structure sheaf of the zero section. Okay, so it's very pretty, very simple. And we define a square root K-theoretic Euler class. And of course, all we do is we take a maximal isotropic when one exists, and we take its K-theoretic Euler class, here it is, as defined on the previous slide. But that is not a good definition, precisely because I could replace lambda by lambda dual, as we've seen throughout the talk, and then I wouldn't get the same answer. But by the usual duality of Cazal resolutions, I can take something precisely in between. So I can take the Nekrasov-Akunkov twist. I can tensor by the, you see, if this square root wasn't there, if I tensor by the determinant of lambda, what would I end up with? Up to sine, I would end up with the exterior power of lambda. So what I do, because I have two choices, I could take lambda or lambda dual, and I'm not sure which exterior power to take, and they differ by tensoring by this determinant. What I do is I go exactly halfway in between. So I tensor by the square root of this determinant, and that again forces me to take these coefficients where I invert 2, because then I can define the square root of any line bundle by just taking the power series definition of square root. I express L as 1 plus L minus 1, and then I just power series expand the square root of 1 plus L minus 1, and I get this. And you check that all the coefficients are integers. Sorry, they all have denominators powers of 2. Okay, and again, there's this sign that keeps cropping up. And so that's our square root Euler class. And more generally, as usual, we work on the cover, where we always have a maximal isotropic. We take this class up on the cover, and then we push it down. And what's interesting is here, the push down can be done over the integers. In this, there's some kind of weird thing that in cohomology, we can define the class over the integers, but then the push down we have to invert 2. In K-theory, we have to invert 2 to even define the class, and then the push down could have been done over the integers. And then we show that these two classes are compatible. You know, if E has a lambda, then this class equals this class. And they satisfy that their square is the Euler class and so on. And again, Keeman-Lee, we use their cosection localization in a K-theoretic context to localize to the zeros of an isotropic section. And we produce a square root K-theoretic Gysin class. So if you have an isotropic cone in your quadratic bundle, then any K-theory class on that cone, we can pull it back to the zero section in a square rooted sense. So again, the way you should think of that is if E has a maximal isotropic and if C lies inside it, then you're just pulling back to the zero section of that maximal isotropic. And in general, that won't be the case, but you can generalize to this. Okay, and in this way, we can define a virtual structure sheaf on the moduli space of sheaves on the Calabi-Yau fourfold.
Question. So,
yes.
Suppose you had the square root of, you know, the square root, suppose you had the square root you wanted. That would be in principle defined over integers, right? And you wanted halves to extract the square root. But it could be
maybe
thing.
like at this stage, for instance.
Yeah, at this stage. Suppose you had a square root.
Like taking this just this line bundle. Yeah, that's absolutely correct. So we proved that once you invert 2 in your coefficients, any square root of this line bundle equals this in K theory.
Right, but well, I'm saying if you had a square root, you don't have to invert 2, right?
Then you don't have to invert 2.
So
let me just think a second. Right, but so then absolutely, then you can define the class, but it's now dependent on your choice of square root.
Right.
What I'm saying is, if you allow me to change the coefficients, then any choice of square root will give the same answer. But if you don't, then that won't be the case. All
right, but then the question is in the situation with the actual sheaves on Calabi-Yau fourfold,
yep.
is that the corresponding square root, does it exist, or?
Well, you're the expert on that. Yeah, I don't know. I don't think so.
Oh, okay.
But it doesn't matter because I'm going to use rational coefficients, or z with 2 inverted. So yeah, I'm not, the invariance I'm trying to get out of these moduli spaces, I'm not going to be able to see 2 torsion invariants. I'm only going to be able to see as rational numbers or something like that.
No, I'm a little worried about this definition you gave, because that kind of assumes that your line bundle is in the neighborhood of 1, which is equivalently not true, right? I mean, equivalently it's it's going to get some weight, and then this series is not clear what the series means.
I haven't thought about that. Oh, yeah, that's a really good point. Okay, I need to think about that.
All right.
Okay, you've ruined my day. Okay. Where are we? So, yes, we can now define this virtual structure sheaf. So what is it? It's just the same as in the cohomological situation. We take this isotropic cone in our bundle E, which the deformation theory gives us. We pull it back to the 0 section of E in this square rooted sense. And now what we have to do is tensor by a certain line bundle. That's just because of, otherwise it's not well defined. So, I'm picking a representative of the obstruction theory here. And as you replace this complex by another complex, which is isomorphic, which is quasi-isomorphic, so you'll change your E, you'll change your T, and so on. And if you didn't have this sort of fudge factor in here, then the result would not be independent of choices. Okay, and so I just end with, finally, you can relate these 2 classes by a Riemann-Roch formula. So in particular, the obvious invariant of the virtual structure sheaf is just an integral over the cohomological virtual cycle of a square root of a Todd class. And because we've got these algebraic classes, they're more computable by torus localization, except Andre has just made me worry that we might have missed something in the K-theoretic torus localization. So I need to go back and check that. But hopefully, since there were no square roots in the cohomological torus localization, I'm pretty confident in that formula at least. So this is if you're used to localization formulae, this looks exactly like the usual localization formula, except all Euler classes are replaced by square roots. So it's very pretty. And similarly, hopefully you can localize the virtual structure sheaf. Okay, so I end there.
Thank you so much, Richard. We have now 24 minutes for questions. So
yeah, great. And as you can see, it's dark here.
Maybe I have a question for Noah. Noah, you.
Is Noah online?
Yes.
Yeah. So So, with these formulas, one then can go and try to. What's the situation with this 4-dimensional box counting? Is that now all proven, or is
No, I was gonna kind of ask you the same thing. So I've been talking a little bit with Richard about this, but I think yeah, it's not totally clear to me yet how exactly to link this with even help C4 or something. With these Nekrasov formulas for help C4.
But that would be an example of this theory in action, right? Is that
that's what I would hope. Yeah. That's my hope. But even in that formula, there are some features that. So there's this extra variable floating around, this y in Nekrasov's stuff, and it's not entirely clear to me how that fits into this picture.
Oh, okay, so in other words, there's something to be done here, which is great, right? I mean,
yeah. So I'm thinking about it, but
okay, all right.
I don't know. Maybe Richard has more to say.
Yeah, on Thursday when we meet.
Okay.
More questions?
Sorry, like you have this ds, which was a map from like if I understand correctly, from first x to second x, right? ds, like go back in your slides, please.
Yeah.
Like.
Is this okay?
No. Later. Yeah, but here. So you've got ds, a map from t to e, and t is the first x, and e is the second x, right?
Sort of. At the point F, that was true. Where S is entirely quadratic or above. In general, away from the point F, this complex computes those X groups. So the kernel is X1, the cohomology in the middle is X2, and the co-kernel is X3. But it is true that at one point, this ds vanishes. And then in that case, you're right, this is X1, this is X2, and this is X3.
And in this case, the map is 0.
Yeah, yeah, that's just at that point. So yeah, that's the, you guys are in Columbia, right? That's Kuranishi. This is the Kuranishi model of the moduli space, is that it can be written to sort of first order about a point F in the Zariski tangent space of the moduli space. So this is the linear approximation to the moduli space. And then there's a higher order, there's a nonlinear map to the obstruction space whose linear part vanishes. So when you restrict it to the origin, it really does vanish. So ds vanishes at the origin. I'm not sure that I'm answering your question though. Sorry, carry on.
Actually, like I wanted to ask, maybe you just answered, but let me ask again, like what is this ds? S was a section on some infinite dimensional space, then it's some one form on this infinite dimensional space.
No, yeah, you shouldn't take this slide too seriously.
Okay.
So I was just telling you there's two ways of writing the moduli space. You can write it in terms of connections and an equation on the curvature. And in that case, you have this infinite dimensional setup. That's correct. We don't do that. We do this everything algebraic. So we take A not to be infinite dimensional. We take A to be this vector space here, which is finite dimensional. And then we use this theory of these guys here to say that locally the moduli space looks like the zeros in this vector space of an isotropic section of a trivial bundle with this fiber. Yeah, that's probably not
So
very
so this ds like this is like ds on this finite dimensional.
Yeah, this is really a finite dimensional thing. There's really an isotropic section of this trivial bundle called S, and we take its exterior derivative. We take its derivative. So. And its derivative makes sense. I mean, we don't have a connection. Well, I guess there is one because it's a trivial bundle. So you could use that. But also ds in algebraic geometry is always well defined along the zeros of S, which is why I've restricted to M here. Then ds is well defined, even without a connection.
Thank you.
Yeah, sure.
Can I ask my favorite question, Richard? Which is, what do you think is gonna, what would be a special feature of counting some sort of curves in Calabi-Yau fivefold? I like to think about this question from time to time, but maybe you have some new perspective on.
Yeah, of course, I think about it from time to time as well, and I have. This gives no new perspective so far as I can tell. So this complex here for fivefolds would have another E here, and then the TA dual would be down here. And this E here would be would be the dual of this E. So it would be a map from E to E dual. And it would either be a skew map or a symmetric map. I can't remember which. And then, one would ask, what can you do with such maps? Is there anything clever you can do with such maps? And I thought about it, but I haven't got anywhere.
Okay, fair enough.
It's a real shame. Your fivefold theory occasionally takes 6 months out of my life, and I never get anywhere with it.
Oh, I'm sorry. More questions.
Is it clear how to compute this this bundle or this like square root of Euler class in examples? So you glue it out of local models, right?
No, it's not clear at all. But so I advocate not trying to do that, but trying to use the torus localization formula. Of course, if your moduli space is smooth, and that happens occasionally, then the X2 bundle over it will really be a bundle, and it'll be a special orthogonal bundle, and it'll have a square root Euler class, and I bet we could compute it in any example. It's certainly true that people don't do a lot of computing square root Euler classes, but I'm sure we could compute it. We could use some topology, but in general, I would advocate using the localization formula.
Okay. Sounds like we're gonna have to end the seminar 15 minutes early, which is fine because we learned so much today anyway. So I think hard to imagine learning more. Thanks, Richard. It's great to see you, and thanks everybody. We'll meet again next week.
Cool. Thanks, Andre.
Yeah, thanks.
Thanks everyone.